little bit more about what I do kind of for a living. I consider myself to be super lucky that I get to explore the universe, and in practice, what I do is try to discover and study very distant galaxies, way beyond our own. And I'll come to that and how, as humankind, we actually realize that our galaxy is not the only one, that is actually quite a recent discovery. And then also try to understand how galaxies like our own, how they form and how they evolve, essentially across more than 13 billion years in time. And fortunately, this involves actually using some of the best telescopes on the ground and in space. So one of my favorite telescopes to use is Hubble, that I've been fortunate enough to actually point it at different galaxies that I've discovered here at Lancaster. And I'll tell you also a little bit more about that. And here, if you can see the slide, it's just a picture of our quite recent group at Lancaster that in 2015 didn't exist, and we're now quite a lot of us. So it's been quite exciting. Now, in practice, and for those that have no idea what an astrophysicist, what he would do or she would do, apart from teaching, I think some of the most exciting things that you get to do is to go to telescopes. So a lot of these pictures are about the things you can see when you go outside a professional telescope, how it looks like when you're actually taking the data, and it's mostly looking at computers and seeing the data come through. Once you process the data, then you can make amazing pictures, like the one you see from the Pillars of Creation. And typically it also involves maintaining the quite high-tech equipment and cooling them down to as low temperatures as possible. So typically this means we need to refill cryostats with liquid nitrogen, something like every 10 hours, so that the images can be as deep as possible. Now, one of the kind of the highlights of what I'll try to explain during the talk has to do with one of the most famous galaxies that I've discovered. So this is Cosmos Redshift 7, or CR7 for short. And the name essentially provides you sort of coordinates of where to find a galaxy on the sky. So Cosmos is actually a very well studied field in the constellation of sextants. And this redshift, for those of you that have attended yesterday's session with Phil, you might already know that redshift is a way that we can use to measure distances in the universe. So redshift of 7 means this galaxy is incredibly distant. But of course, one of the reasons why this galaxy became so famous, not only because it's really beautiful, and I think it's super nice, it's also because when we discovered it, we explicitly put the acronym so it would resemble another CR7, which was already very well known, which is a football player. So this really helped with outreach and actually getting astrophysics in BBC Sport or CNN and a lot of news outlets. So for the rest of the talk, and in terms of the research that I do, and I'll also explain, if you're interested, how you can actually do at least part of the research with some resources that we share online, is to try to address the question where we come from, and also what we are made of. And I really like this photo because it was taken by 4 of my students when they went observing, and I think really captures kind of the essence of what it is to be human. We do not produce light, not visible light at least, and essentially against the background of stars, we are nothing but essentially darkness. But over the last hundreds of years, actually by working together, we can now look up and not just see something that looks beautiful, but actually make sense of it and answer those 2 fundamental questions of where we come from and what we are made of. And so these are also key questions that we try to address here at Lancaster. And I think one of the most fundamental things, even if you don't understand the details, is perhaps just grasping the fact that, especially now during the lockdown, where the sun is out every day, apparently when the economy was going okay, it would rain, but now it is sunny all the time. So if you were to go outside and actually essentially split or disperse the light of the sun into blue all the way to the red, apart from seeing a rainbow, which you can see if it's raining and the sun's shining, but you can also see all these dark stripes that actually extend all the way from the bluest kind of waves to the reddest. And those dark stripes are actually quite fundamental. And essentially, they tell us about the chemistry of the sun, which is actually shared among all the planets in the solar system. So to put it in a simple way, this kind of tells us what is our cosmic DNA. And I think one of the major discoveries of the last few years has been to understand that this cosmic DNA is different depending on the solar system you're looking at. Each solar system actually has unique chemistry. It has different amounts of iron, carbon, or oxygen that you can actually measure by seeing how strong these dark stripes are. So it is important to understand that we stand on a specific solar system, and that's essentially dominated by the sun, and we're characterized by specific chemistry. Now, it's really great that nowadays we can actually answer the question about what we are made of, and essentially what are the fractions of us that are as old as the universe is, which ones were only made afterwards, and which kind of processes actually made different parts of us. And we usually say that we're made of stardust, and that's definitely true. About almost 90% of us is made of stars that have died. And it's only about 10% of us that comes directly from the Big Bang, essentially the moment of creation of our universe about 13.7 billion years ago. Most of it, and essentially every single oxygen atom that allows us to keep breathing and stay alive, actually comes from exploding massive stars that live very short lives and that actually are responsible for the majority of things that make us and allow us to live. And it's only the remaining about 16.5 to 17% is made of other kinds of exploding stars that take much longer to detonate. But they are important, for example, because they produce most of the iron in our blood. Now, to think about the universe in the past is actually think about a universe that was way, way simpler. So if you were to go to the very beginning of the universe, chemistry essentially didn't exist. Chemistry was not born with the universe, and so were all the other areas. The only thing essentially in science that was born with the universe, I would argue, was physics, and obviously all the mathematics that you can explore with it. And it means that when the universe was born, there were no ingredients to form planets or life, and we were completely impossible. Now, the good news is back then, everyone would have straight A's in any exam that you take in chemistry, because chemistry was so simple. I mean, you could actually memorize the periodic table without much effort. It only contained essentially 3 and a little bit of the 4th element. It was mostly just made of hydrogen, helium, a little bit of lithium. And it was only because the conditions were right for the first stars to form. And these stars actually were quite unique because they were just made of hydrogen and helium, while stars like the sun have all those dark stripes because they also contain carbon and iron and all the other elements. These stars did not. But that's okay because they're the ones that were able to actually create them for the very first time. So these stars, we think, they only existed in the very early universe because they were only made of hydrogen and helium. And we think that they were incredibly massive and incredibly luminous. So you can see in the slide kind of my own very simplistic comparison between the size of our own sun and the size of a typical first generation star just made of hydrogen and helium. So it would be much bigger, much more luminous. If you were to put a planet like the Earth going around one of these stars, essentially there's no amount of solar or sunscreen that would save you. So you wouldn't just get burned, you would actually be ionized, destroyed, because of how intense the radiation was from these stars. The good news for us is that they only lived for a very short amount of time, and they actually exploded as a supernova. And this was essentially the moment when chemistry was created in the universe. And they were responsible for creating the first traces of heavy elements. So something like 5 to 6% of the carbon and oxygen that is in our bodies was actually first formed in these very early generation stars. They didn't produce much, but they produced the first ones that allowed subsequent generation of stars to then create the rest. And they essentially changed the nature of the universe completely. So after they exploded, for example, planets became possible because you could actually have the building blocks to do them, and before they couldn't. So I'd also argue, whenever someone asks me what has astronomy done for economic impact, and I would say astronomy is the reason why there's economy, because without the very first stars exploding, there would be no heavy elements and no life and no economy. So it is a very good way to also give us perspective on where things come and how this ties in our quest to understand our cosmic origins. Now, the other thing that we've realized as stars kept forming throughout the history of the universe, we've realized that depending on whether a star is something like the sun that you can see in the top corner, or a very massive star, they have completely different properties. So to begin with, you might see that a star like the sun looks more yellowish, while a very massive star is very blue. But on the other hand, these very massive stars actually evolve very quickly. They become these red giants very, very quickly. And actually, these are the stars that end up exploding as supernova. So what we've learned is that throughout then the history of the universe, the elements that are crucial for us to survive and to live and that make our planet, most of them were created in these thermonuclear explosions. And we've realized somehow that in the universe, it's the massive stars that actually pay all the tax, all the kind of heavy element tax, while stars like the sun, which you may see now just becoming a white dwarf at the end of its life, they still produce heavy elements, actually carbon and oxygen, but all the heavy elements stay locked in a core. So actually they produce heavy elements, but unless you do something to the stars, they never share it with the universe. So in a way, stars like the sun are big tax evaders, and big, massive stars pay a lot of tax and allow us to essentially breathe and stay alive, which is great. If you do have any questions, and again, I'll ask Phil to stop me, and if not, I will carry on.
There's no questions in the chat yet, David, so we're okay. Great.
That's great. And I hope the pace is okay as well, and that the sound is coming out okay. Now, coming back to this image that I really like, and I would also try to motivate you on the importance of kind of looking up, especially if you're privileged enough to experience a sky like this. So this photo is actually taken in La Palma in the Canary Islands, where some of the largest telescopes in the world exist. Actually, the record holder for the largest optical to near-infrared telescope sits on this mountain. It's a 10.4 meter telescope. That's really impressive. And if you're outside in a night like this, where the moon was not out, you can very easily see with your own eyes the disk sort of extending across the sky. That's our cosmic home, the Milky Way. And among all these stars that seem like a lot, but actually we're just seeing very nearby stars to us because our eyes are not the best telescopes. And among all these bright spots in the sky, actually there's this one thing that our eyes can capture and that has been captured in this image that is not within our galaxy or in the local neighborhood. And that is just to the top left of the leftmost person. You might see there's a smudge of light there. That is Andromeda. It's a very big galaxy, even bigger than ours, that's coming our way ferociously, and that will kind of merge with ours in something like 6 billion years. Now, if you, like me, you essentially, all you do is to try to discover and study other galaxies beyond our Milky Way, you might think that that it's kind of frustrating because when you look at the sky, there's just one galaxy. And throughout the history, essentially, we thought that it was even less than that. So it took us quite a long time, essentially up to the 1900s, to really understand that we do live in a galaxy. So you can think of it as a big island of stars, something like 100 billion stars in our galaxy. But galaxies are not just made of stars, they're made of dust that you can see, all those dark kind of clouds. They're actually dust that's obscuring the light that comes from stars. Actually, galaxies, most of the mass is in the mysterious form that we call dark matter. And then there's all kinds of planets and black holes and everything else. And our galaxy measures something like 100,000 light years across. So this means that if you live in one side of the galaxy and you want to send some message to an alien friend on the other side of the galaxy, that message will literally take 100,000 years to get to that alien friend. And it would take at least 200,000 years for you to get a reply if they were to reply immediately. So I think it is very important to have this notion of scale just in our own galaxy, and also just how hard it is, even if we ever find alien life or civilization, to establish contact, because nothing can travel faster than the speed of light, and the distances are so big that it takes a really long time for light to go through the galaxy. Now, you could think that a galaxy is something big, and in the 1900s, at the start of them, people thought that a galaxy was so big that it had to be the entire universe. So even back then, if you were to think about the volume that we occupy in the galaxy, that is just one part in a number made of 63 zeros. So it's already excruciatingly small. We were already incredibly insignificant in the face of our galaxy. And that's one of the reasons why people thought that there's no way the universe could be larger than a galaxy. I mean, the scale of a galaxy is already so hard to grasp. And essentially, I think that's one of the reasons why, even though we had actually discovered other galaxies, no one could believe that they were other galaxies, because that would imply that the universe was way larger than we ever thought. So in the early 1900s, actually people had already taken some of the first photographs of Andromeda. That's on the top left. And also on the top right, they weren't quarantined, but because they didn't have social media, they had a lot of free time, some of the astronomers, so they would actually draw by hand. And this is an actually hand drawing of one spiral galaxy that you can see with a decent telescope. And back then, people thought that these strange things that they call spiral nebula, they couldn't be distant galaxies because that would mean they would have to be really far away. So astronomers, and something like 99.9% of astronomers that would get together to discuss these things would agree that what you were seeing was a solar system information. That essentially the reason why you couldn't see individual stars was because the star hadn't been formed, and that essentially if you were to wait long enough, this kind of disk would fragment into planets, and at the center you would have a star like the sun. And it's quite interesting to understand that people kept thinking that was the case. And back then, unfortunately, humankind was only using a fraction of our total brain power because science was mostly dominated just by men. And it turned out that it was a woman that at the time would not be considered more than a human computer, unfortunately. She actually made one of the biggest breakthroughs in science ever, essentially by understanding and actually figuring out a way to measure a distance to these things. So she's essentially the discoverer of the first major cosmic ruler, essentially a ruler that you could extend and measure accurately the distances to these things. And I always find it curious that she was born in Lancaster, but on the wrong Lancaster on the other side of the pond. And essentially, she allowed people to establish these things not as solar systems information, but as kind of islands of stars in their own right. And the reason why you couldn't see individual stars was because of how far away they were, which meant that the universe was way larger. And unfortunately, Henrietta Leavitt and her work is not as well known, but it is becoming more well known. And I was really privileged just over a couple of years ago to when I was visiting Harvard, the Harvard Smithsonian Center, and giving a few seminars. I finally got the chance to visit the place where Henrietta did all that breakthrough work. And essentially, it's because of her that I can do what I do. Essentially, she invented my area of research by allowing us to start looking at galaxies beyond our own. Now, I think one of the big reasons why she didn't get all the credit, on one hand, is because she was working in New England, and New England, just like England, most of the nights are cloudy and the weather isn't that great. But on the other side of the US and the West Coast, and specifically very near Pasadena and Mount Wilson, someone else actually took advantage of what Leavitt discovered inside this telescope to make an even more fundamental and kind of transformational discovery. So that person is very, very well known. He even has a space telescope named after him, even though kind of all he did was to sit on this chair that is actually still there inside the telescope, the original chair, the original telescope. And all he did was literally just apply the technique that Henrietta Leavitt discovered. And he started measuring distances to these different nebula. And this really allowed him not only to establish that the universe was really, really big, but also by linking some observations that someone else did, but he forgot to give them credit as well, to understand that somehow the more distant a galaxy is, the faster it is moving away from us. And this became known at the time as the Hubble law. And Hubble, when he published, this is the graph. This is kind of the graph that transforms the way we see our universe. And essentially, on the horizontal parts, this is what Hubble measured using Henrietta Leavitt's technique. Essentially, distances in astronomy, we measure them in parsecs. It's just, if you don't know what a parsec is, it's just a lot of kilometers, like a lot. And by combining measurements from someone else, you realize that the further away something is, the faster it's moving away from us. And what that meant was that not only was the universe much larger than we ever thought, the universe is actually expanding. This is what it means for something, when you look further away, to be moving faster away from us. And I always use this plot also for Lancaster students to show how someone as famous as Hubble, I mean, if you get a space telescope to be named after you, I would say that's really peak fame in astronomy terms. How someone like that can make so many mistakes in a single graph. So on one hand, one of the big mistakes that Hubble did was to write velocities as kilometers. This should have been space divided by time. I mean, you never go to your car and you see a velocity as 5 kilometers. It's kilometers per hour or per second. On the other hand, actually, Hubble took those measurements of velocity from someone else without crediting. That's nowadays called plagiarism. And to top it off, actually, Hubble, when applying the technique discovered by Henrietta Leavitt, actually made a big mistake. So all the distances were off by something like a factor up to 20. Right? So even though he made all these mistakes, it still became incredibly world famous and got a space telescope named after him. And I think this tells us two things. One is all scientists make mistakes, and including and especially the really famous ones. And on the other hand, even if you make a big mistake like this in science, it can still transform the way we see the world. So even after correcting all the mistakes, the basic result that the universe is expanding still holds, and still holds now. So essentially, after making this first step in the early 1900s, until now, where we can explore the universe all the way to kind of the observable edges, we now know just how insignificant we are. And if you're bored because you're kind of isolated and in quarantine, it's always good to top up how humble we should be in face of the universe, to just write how insignificant we are. And you can achieve that by, you can write a 1, that's you or me, and then you can write a number. You can start with a 1 and then count 84 zeros. And if you divide 1 by a number made of 84 zeros, this is our cosmic insignificance. And of course, it gets better because the universe is not only extremely big, but it actually keeps getting bigger every second. So our cosmic insignificance becomes even larger. But it also means that there's huge opportunities. The universe is so big that it's very hard to run out of things to discover. And I think this is one of the most exciting things in what I do. The other part, and to be a little bit more optimistic, is that essentially, in spite of how insignificant we are and the fact that we only live for a very small fraction of cosmic time, just in something like 100 years, we have achieved so much in exploring the universe beyond our own galaxy. And it means that is not a preventing factor from essentially exploring the whole universe, even if we're kind of stuck, not only in our planet, but also kind of stuck in our homes for the moment. And perhaps one of the most spectacular discoveries that has been made over the last decades has been to look, if you see the arrow on the slide, and a very tiny point, right? So you can imagine the next time you look up, just a point in the sky where there's no visible star, and that is incredibly tiny, like a pixel. A few years ago, somehow a bunch of my colleagues were able to convince the committee and NASA to essentially point the Hubble Space Telescope. It's incredibly expensive, but actually point it at a place where it contained nothing that we could see for weeks. And when we did that, we realized that even though to our eyes, a single point in the sky may be deserted or contain no stars at all, if you point Hubble, this is what you see. And specifically, once you start measuring distances to the different galaxies, you understand that these tens of thousands of galaxies in every point actually span a huge range of distances, all the way to more than 13 billion light years away. And if you do these experiments and you point at the sky in different places, and you try to count all the galaxies that there should be in the observable universe, the current best estimate is that there should be 2 trillion galaxies. That's a number with 12 zeros. So it really means that if you ignore any funding problems, me and my colleagues will never go unemployed, because we will never run out of galaxies to discover. And it's also good to understand that galaxies contain so many stars and so many planets that we expect that in the entire universe, there's as many as something like a septillion stars and a septillion planets. That's a number with 24 zeros. So planets like the Earth are certainly out there, but the problem really is the distances and trying to find them. So essentially, with this background, these are some of the fundamental tools that I use daily to try to explore the distant universe together with some of my students, and to discover the most distant galaxies and trying to time travel back in time. Are there any questions up to now?
There's no questions at the moment, David, but I'd like you to ask us to think, if there's so many galaxies in the sky, why is the night sky dark? Why is the night sky not bright with all these lights coming from all these galaxies?
It's a good question.
So yeah, I thought that was a good provoke.
Yes, and I mean, sorry. Yeah, and that's one of the questions that people thought about a lot, and there's quite a lot of reasons for it. Well, one, in the UK, the sky is not full of bright things because the sky is mostly cloudy. That's a very easy way to explain it. But in the darkest skies, actually, even though there's so many galaxies, they're not infinite, so they don't really cover the entire sky. But most importantly, a lot of the galaxies are actually so distant that, for example, their light starts being redshifted. So galaxies like, I'll tell you, CR7 actually are completely gone to our eyes. The light has been so much stretched by the expansion of the universe that even the bluest light has gone away from the optical. So there's a combination of reasons why, even though there's so many galaxies, for you to see it, you really need a big telescope, and you really need to kind of integrate to collect all these light particles for a long time before you see them. They're very faint, even though they're very numerous. Tim, do you have any questions?
We've got a question from Steve. Are super distant galaxies evenly distributed in all directions?
That is a very good question. So this is something that we actively try to investigate, and the results show that there are not. So the brightest and the most massive galaxies are actually very clustered on the sky. And typically, so galaxies like CR7, some of the brightest in the early universe, they actually pinpoint to places that are going to end up as clusters of galaxies. So they're kind of very biased regions where there's a lot of mass and a lot of other galaxies will form around. So they're definitely not evenly distributed in the sky. And this is one of the big reasons why it's kind of very hard to find them. And you need to survey big chunks of the sky before you're kind of lucky enough to find one. You can't just sample a tiny little area like the one in the Hubble Deep Field to find these galaxies. You need very big chunks. So, and this is actually, yes.
Another question coming in from Ben. You say the universe is like a thing or an object, and you say it is expanding.
Yes.
So my question is, what do you think the context, the background of the expanding object is? What is it expanding into?
Yes, so that is an excellent question. And as far as we can tell, the universe is not expanding into anything. So it's really, the best way to think of it is that it's the fabric of time that is actually stretching. So it's as if you have if you think of space-time or just space as some sort of rubber, and you're just stretching it, and we are all in its surface. And because of the way we experience space-time and because of what we know about the universe doesn't have to be expanding to anywhere, because this is just how it is. And so perhaps the best way of dealing with this is to get away from this analogy of the universe expanding like a balloon. I think this is very misleading, because the balloon is expanding into something. It's expanding into a room, for example. And actually in a balloon, there is a center. So perhaps the best way of thinking about it is thinking of the universe as a grid. And one of the nodes of the grid, this is where our galaxy is. And galaxies can be in different kind of nodes of the grid. And what happens as time goes on is that essentially the grid is just becoming larger. So the distances between the nodes are increasing all the time. But just to make it perhaps more confusing or more kind of mind-blowing, the universe at the start could have already been an infinite grid, just that the nodes were incredibly close. And as time went on, the nodes are becoming more far apart from each other, and we perceive it as an expansion of the universe. And I know it can be mind-blowing to think that the universe would be, that this grid would extend to infinity to begin with, but if you do that, then I think you could think more clearly that the universe doesn't have to be expanding into anything. It could just be a grid. And what we're seeing is the nodes getting further apart. So this is the simplest, best explanation that I could give to explain how we see the expansion and growth of space-time.
Okay, David. Well, Tim's okay. Go.
The question I had was actually concerning dark matter.
Yeah.
From all you've said, it appears that dark matter is essentially transparent. Is that true, or is dark matter hiding something that we can't see?
Yes. So what it means, we call it dark matter because it does not interact, for example, electromagnetically, which would allow us to see it. And as far as we can tell, it only interacts gravitationally. So we can see the kind of gravitational pull that it has. We know that it kind of dominates on scales of galaxies. So we know that, for example, what holds galaxies together, most of them, and also clusters of galaxies, is actually dark matter. It is not the luminous matter that we can see. And in terms of whether it's transparent, because it does not interact and does not absorb light, it is by definition transparent. It is not hiding anything, really. And in principle, dark matter is everywhere. So we should be essentially being bombarded with whatever if dark matter is a particle, with dark matter particles that just pass through us. But essentially, they're at very low density when compared to the mass that makes us. So we definitely wouldn't realize that that is the case. But dark matter is kind of spread throughout the galaxy and in a much more spherical way. So dark matter does not get distributed like a disk, like ordinary matter. And it cannot do that because it cannot lose energy to form a disk. And you can think it more as a halo that extends way beyond the stars. So the scale of dark matter in galaxies is way larger than the visible mass.
Okay, David, some more questions coming in.
Yeah.
There's 3 questions. First one is, what part of the EM spectrum is used to detect galaxies?
Mm-hmm. Yes. So the part of the electromagnetic spectrum that is used to detect them, when we talk about galaxies, typically mean we're detecting them because of the light from stars. So this means typically the ultraviolet, the optical, and the near infrared. But actually, in my research, I even use X-rays because they allow us to trace the activity of supermassive black holes, and also all the way to the radio. And in the radio and closer to it, we have access to the coldest temperatures that we can see in the universe. So the universe doesn't get as cold as Lancaster. We still hold the record in the universe as the coldest place, but we access temperatures very close to the 2.7 Kelvin. That is kind of the roof temperature in the universe. And that allows us to study, for example, the clouds that eventually collapse and form stars. They're incredibly cold and dusty. And for you to study and see them, you need to go into the region of the electromagnetic spectrum of very large waves, like the far infrared, the submillimeter, and also the radio.
Okay, 2 questions. I'll take these together, David.
Yeah.
But one question is saying, are you saying then that the universe is infinite? And the other question is, do you think there is a limit to how far the universe can expand?
Yes. So in terms of whether the universe is infinite or not, we cannot tell, but that is possible. So what I meant is, it is possible that the universe already started as infinite and you can still have a Big Bang. Now, the observable universe is finite because it is determined essentially by the age of the universe, allowing us to see just as far as the time as the light as at time to get to us. So the observable universe has a radius that is the same as the age of the universe in light years. So the observable universe, wherever we look, is essentially 13.8 billion years old. That is the limit. So essentially, at that limit, we're seeing when the Big Bang happened. But that doesn't mean that the universe doesn't extend and that it may or may not be infinite. And the question of whether there's a limit to which the universe can expand to, we also do not know. What we know is that the universe isn't just expanding. Somehow, over the last billion years, this expansion started to accelerate. So if anything, it looks like the universe is growing even faster, and the expansion is getting faster every day. So that doesn't seem to be a limit. And there's just big discussions into what will happen if this expansion rate keeps going up. And I guess one of the worst case scenarios is that something like in a trillion years, my job will not exist because it will not be possible to see distant galaxies, because the expansion of the universe will actually be happening faster than the speed of light. And therefore, the light from distant galaxies will no longer be able to get to whatever is left of our galaxy when it merges with others here.
Hey, David, you've got to ask the question after that. They're saying we're told that there's nothing can travel faster than the speed of light.
Yes, that is true. So I think this is really important to understand that when we measure that a galaxy is moving away from us, it is actually not moving. Galaxies are they're stuck to these nodes in the grids. What is happening is the grid itself is growing. And even though you cannot move from one node of the grid to the other at a speed faster than the speed of light, there is nothing preventing the grid actually to expand at a rate faster than the speed of light. So space-time can, in principle, essentially expand at a velocity that is faster. If that happens, it means information will not be able to travel from one point to the other anymore. So that has not happened yet. But if the expansion of the universe keeps accelerating, it will happen inevitably.
Okay, no more questions at the moment, David.
That's good.
Are you okay?
Yeah.
Do you want to take a break? Or are you fine to move on?
No, I'm okay. People are okay. I can carry on, and you can also always shut me up if I'm going for too long, or just ask any questions as we go. Yeah.
Okay. There's no questions at the moment, so after.
Perfect. Yes. So I think what I could try to tell you is essentially how we use the best telescopes in the world to essentially try to go back in time and study how the universe was when it was much more primitive. So sort of trying to use a time machine and essentially look at how galaxies look like when the universe was much younger. And this kind of gives us this kind of artistic impression, tells in a very simplistic way, the history of the universe from the Big Bang, when the universe was incredibly compact, but it might have been infinite. I know it can be very confusing. When it expanded, where we actually have the formation of the first atoms, and we can see the relics of that moment with the cosmic microwave background that you can detect with a simple antenna, and something like a few percent of the static noise will come from that as an incredibly old relic. Then the formation of the first stars and galaxies, all the way to us. And we can use very big telescopes to essentially find distant galaxies. And because the information took so long to get to us, when that information gets to us, it tells us about how the universe was when the light came out. So it means that if you find a galaxy that's 13 billion light years away, you can know how the universe was 13 billion years ago. And this is essentially how it works. So one of the most famous experiments that I've done, and this has been as part of my PhD in Edinburgh, was to try to measure what is the economic activity of the universe as time went on. And for the universe itself, what you want to measure is, in this case, the tons of stars produced in a given volume of the universe. And I made this calculation in terms of essentially per minute. How many tons of stars were produced in a cube made of 1 light year per minute, and also how that varied. And you can really think that this is a kind of economic measurements, because the stars that are being formed, they will go supernova. So they will literally produce the heavy elements that are contributing to the kind of the universe economy. And to do that, I was really lucky that I was able to escape the weather from Edinburgh every 6 months and travel to Hawaii, and typically spend something like 6 to 10 nights at this telescope that is still called UKIRT, the United Kingdom Infrared Telescope, even though it no longer belongs to the UK, because the UK wanted to get rid of it and even paid for a consortium to actually take it over. And that was really unfortunate, because it's probably one of the best telescopes at the time. And it really allowed us to see way, way back in time. So what I did at the summit, it's very, very high. it's probably the best place in the entire planet to observe the distant universe. The conditions are just right. You're above most of the atmosphere, and the atmosphere is really stable. So what I was able to do, not only using UCERT, but also telescopes in Chile, and another telescope owned by Japan, just on the other side of the Hawaiian mountain, was to measure this and to actually establish that about 11 billion years ago, there was a peak of star formation in the universe as a whole, where the universe was forming something like 30 tons of stars per cubic light year per minute. And nowadays, it's just forming 1 ton of stars per cubic light year per minute. So it means that something happened and kept happening over the last 11 billion years to lead to something like a 30 times economic downturn. And actually trying to understand why this is still one of the big open questions, whether there was some sort of cosmic event, or whether it's to do with the physics of galaxies, or galaxies running out of fuel. And we think actually, and maybe people have questions about this, but we think that what's happening is a combination of actually a lot of factors. But it is important to understand that the universe was most active 11 billion years ago. And even though stars still form, even in our own galaxy, this is just 1/30 of what it used to be if you were at the peak production of stars, and therefore heavy elements. So after establishing
Question
this,
for you, David.
yeah,
Nice little question for you. Does UK IRT take visitors?
Yes, I think they still did. So every time I would go there, I would try to show it to anyone that would actually be around. If anything, people will have to sign a waiver because it is quite high altitude. And in the US, they're particularly worried about people suing them because at high altitudes, you have to be really careful about the level of oxygen. They definitely do. And the same thing applies to telescopes in the Canary Islands. So if people contact the local observatory, it is often more than possible to schedule a visit, and it's definitely worth it. I mean, Hawaii is way more far away than the Canary Islands, but I think the experience is also very, very different. And to me personally, it's even nicer. So I think the only problem is actually visiting telescopes in Chile. The ESO telescopes are a little bit more complicated because technically the telescopes sit on international land that is no longer, or it is not owned by Chile, or at least for a few years. So it is a little bit more complicated, but telescopes in Hawaii are easy to visit. So after establishing this, the next goal that I had, and essentially for the rest of the talk and leading to the discovery of the brightest distant galaxies, was to try to push this. So somehow there was a peak of activity of the universe, essentially like 2 to 3 billion years after the universe started, or 11 billion years ago. So we wanted to understand what happened just before that peak, and essentially what kind of galaxies there were out there, how they looked like, and somehow what kind of physics was going on inside them. And to do that, it becomes even more complicated, and you need to use even more powerful telescopes than UCERT, that is a 4-meter telescope. So you really need the larger ones. And typically, it means going to observatories for quite a lot of nights. And in this case, this is one of the aspects we do in the Isaac Newton telescope. And when it's dark enough, typically we point at fields in the sky that are away from our own galaxy. So this is one of the fields that we study the most, that is quite dark in the sky, next to the constellation of Sextans. And this is what is known as the cosmos field. So it occupies the area on the sky of a few full moons. And if you zoom in with some of the best telescopes, obviously you find still quite a lot of stars, but most importantly, you start discovering a lot of distant galaxies. And one of the reasons why we study this field, others also in the sky, is because pretty much every single professional telescope has looked at it, which means that we can really use the information of the full electromagnetic spectrum. Right? So not just focusing on the visible, but actually all the way from the X-rays to the radio. All those wavelengths are available in the cosmos field. So typically it means pointing telescopes like this. So this is an actual footage of a night for our time traveling that is the closest. So the closest distance from the experiments that we were doing over the last few years has been 11.3 billion years ago, where we built specific filters that we put in front of a camera. The camera on these telescopes is typically at the very top. So it sits in something we call the prime focus, which gives us the larger field of view. So it allows us to scan big areas in the sky. And essentially what we do is we cover fields like cosmos and others many times, kind of the full moon in the sky. And we use different filters, and each filter is kind of tuned to go back in time by a specific amount. So in this case, this filter goes back in time 11.3 billion years. Others will go to 11.5, 11.7, all the way to 13. And essentially what these filters are sensitive to are processes that happen, for example, in our own galaxy, but we're seeing them in incredibly distant galaxies. So I'm sure you've seen pretty pictures like these. Typically, they look very red. And that is because the hydrogen around these regions is being excited or heated. And actually, when it tries to go back to its natural stage or state, it emits some red photons. We call them age alpha. But they also emit some very blue photons that our atmosphere simply doesn't allow us to see. And this happens because within these clouds, there's these very massive stars, the ones that go supernova, the ones that produce the oxygen. They actually are hitting the clouds, and actually they're breaking the hydrogen atoms apart. And when these atoms come back together, they emit these photons. A lot of them are red, but a lot of them, what we call Lyman alpha photons, are very, very blue. We just don't see them with our eyes because they're in the ultraviolet. Now, if you look at extremely distant galaxies, they're so far away, and apparently they seem to be moving so fast from us that these ultraviolet photons get stretched. And they get stretched so much that even though when they got out of the galaxy, they were ultraviolet photons, when they get to Earth, they're in the optical. And we design these filters to get those photons when they get in the optical at different wavelengths. And perhaps the best way to see this in practice, so this is actual real filters that we use to find some real galaxies in the cosmos field. So this is the kind of the visible spectrum and extending a little bit more into the infrared and a little bit into the ultraviolet. And essentially, every time we use one of these filters to the sky, if a galaxy is at a specific look back time, it shines brighter in that filter, and it doesn't shine brighter in the other ones. So we know by essentially taking images in the sky with all the filters, whenever we see a specific galaxy become brighter in one of these filters and not in the other ones, we know essentially how far back in time we're looking at. And we don't just do this kind of galaxy by galaxy, we do this over the full cosmos field. So these are real galaxies, and essentially how they look like when we look through the different filters. So what you're seeing here is essentially the techniques that we use, and when we observe in different filters from the blue to the red, whenever we find galaxies at a given distance, they become brighter in the sky. And it means we know how far away they are. And this is how we can transform images with different filters to an actual 3D map of the universe in a very, very efficient way. And so this is, for example, how we produce this three-dimensional map that we called SC4K, or Slicing Cosmos, and with 4,000 galaxies, where with different filters, we're able to get a different slice of cosmic time, where on top you can see how much far back in time you're looking at, from something like 11 billion years ago to almost 13. You can see how galaxies look like in the sky. And then when you use the information, you actually get a 3D perspective. And it also means that for every one of these essentially circles, we can actually go there and study them individually with the Hubble Space Telescope, looking at the X-rays and radio at the full electromagnetic spectrum. So it also means that we can see how galaxies, at least on average, how they're evolving from something like 13 billion years ago to the peak of activity in the universe. And so this is one of the major discoveries just a couple of years ago. And when we published, this is one of the largest samples of these incredibly distant galaxies, with the added advantage that we have the full information to study the physics of what's going on in these galaxies. And again, this also conveys the fact that the galaxies that appear redder is because they've been redshifted the most, and means they're at the longest distances. The other thing that you might ask me as well is, if you look at the distance in billion light years, you'll see that these galaxies right now are actually at distances that are more than 13 billion light years. And that is because even though the light has taken something like 13 billion years to get to us, while the light kept traveling, the universe kept expanding. So really, the galaxies are even much further than they were when the light started traveling towards us. So some of these galaxies are almost, in terms of real distance, of something like 30 billion light years away. So it's quite astonishing. And it also means that because we have images of the Hubble Space Telescope, we can even produce zoom in. So these is all the galaxies we've discovered. They're all incredibly far away. And you can zoom in, but you can also see that even with Hubble, a lot of them just look like a few pixels. And that is because they are so distant. Yet some of them, you see that they look a little bit more white, others are shades of blue. And it means that different physics is going on inside these galaxies. And if you want, at the end, the link is throughout the slides in xgal.uk. You can actually discover these galaxies yourself and understand some more of the techniques behind them, and also actually study them individually. So we try to make this with YouTube tutorials. They should be very easy to follow. So as the final thing, and leading to the discovery of something even more distant, so with Slicing Cosmos and 4K, or SC4K, we go back in time to something almost like 12 billion light years, or the light has taken 12 billion light years to get to us. But we're actually able to extend this technique to go even further. And it's basically just me and 3 PhD students at the time. So whenever you hear that big discoveries can only be done in like huge teams that require trillions or millions of pounds, sometimes you can still make a really big breakthrough with 0 pounds and just a few people working passionately and trying to do what others just didn't dare to do. This is the actual kind of print screen of the data. So just a small chunk of it in the sky, taken with one of our filters, and almost in the infrared, actually, that is sensitive to light that's been redshifted something like 7 times. And within this, there's a blob that you can see with a circle that to your eyes probably doesn't look any different from other blobs. There's quite a lot of them like this. The big difference is almost all the other blobs around are very nearby galaxies. So they're nearby, to me, it means maybe 1-2 billion light years away, while the blob in the center is right now almost 13 billion light years away. And the reason why this blob looks the same as the other ones is because it is intrinsically extremely, extremely bright. This is the only way that you can have something like a car that's just in front of you and a car that's in America, and if both things look with the same apparent brightness, it means something in America is like a nuclear bomb. This is the only way you can do it. And also in the xgal.uk, you have an activity where you can use this actual data, so the real data, to discover this galaxy, and then apply the techniques to discover other galaxies and submit to us. So when we looked at it with Hubble, this blob actually breaks apart into these 3 different components. So this is the galaxy that we nicknamed CR7, or Cosmos Redshift 7. That is actually a merger of 3 galaxies. One that's the brightest, that's component A, and then there's C and B, and the blob that you see in the image is actually the green light. It is actually, you can think of it as a huge star-forming region. Those images that you'd see in red, really beautiful, but in the scale of an entire galaxy. So these are the UV Lyman alpha photons that have been redshifted and captured by our filter. So these galaxies are incredibly rare. We've now been able to kind of find more of them, but within areas like the full moon, you expect less than 1, actually. So it's only by surveying really large chunks of the sky that you can actually find success and find some of these galaxies. So if you Google CR7, you might encounter even the wiki page that people did this. This was also part of some war between Messi fans and Ronaldo fans that were fighting over the galaxy and the fact that Messi didn't have a galaxy named after him. And you'll see that the description of what Cosmos Redshift 7 stands for, and also how we discovered this using both the Very Large Telescope at ESO, but also crucially the Keck telescope in Hawaii that we use to confirm the distance. And CR7 still holds the record for the brightest galaxy in the early universe. And it's something that people just didn't expect to exist at all. And it also means that because it got so much media attention, there was even a team from Japan, from NHK, kind of the equivalent to BBC, that came to Lisbon a few years ago and made a full 1-hour documentary, and also worked with us to make a 3D artistic impression of how it would be if we really went there with a time machine and we could navigate over the different components of the galaxy. And we now know even more than when the documentary was made in 2016, because we've observed the galaxy also in very long wavelengths with the largest telescope, the largest radio telescope in the world. So we now know even some of the chemistry within these regions in CR7. We know that within them, there's already some traces of carbon. So it's only something like 1 to 10% of the carbon that exists in our own sun. But it means that some of the first generation stars have already exploded. And it means that this is the galaxy that is providing us kind of the sharpest view of how very early galaxies assembled and formed. And also, we now have a very good indication that if we could see how the galaxy looks like at the present, it should look like a big, massive elliptical galaxy sitting in the center of a galaxy cluster. But we're seeing it just as it was kind of forming in its very, very early stages, which is really exciting. So the other consequence of the galaxy being so famous and so important for discoveries is that it also features in the official documentation and webpage for the successor of Hubble. So it's really cool to have something you discover there. And I always try to make the case to NASA that because CR7 occupies one of the 19 elements and the mission is costing more than 10 billion, we should have our fair share. But my arguments have not been heard. So obviously we have not got any funding, but we do get the privilege of, even though it won't be us that do the observations, CR7 is going to be one of the first targets when JWST launches. So the successor to Hubble with a mirror of 6.5 meters that is actually shielded in gold and that will be launched next year. One of the first things it will look at is it will be the galaxy that we discovered. So it's really quite exciting, and we think we'll discover even more things within this galaxy that probably we weren't completely expecting. Now, apart from that, we didn't stop when we discovered CR7, and we wanted to know. Yeah.
Can I before you just? There's a few questions.
Oh, sure. I'm almost finishing as well. Yeah. Well, let's take questions.
The one is actually from Sue, who asked. She's already asked you before you showed the slide. Have you got access to James Watt telescope? So you've answered that question. Somebody is asking, Hazel's asking, can you send the link of the tutorials that you've been talking about?
Yes, I can even demonstrate how to use them. So I was planning on just at the end just showing the web page and very simply how you would do them. Okay,
Hazel. So you'll get the web page.
But it's xgal.uk. So if you go to xgal.uk, it's a simple link, and then there's a tab for xgal DIY for do it yourself, and it explains everything.
Would you put that in the chat, David, when you've finished? So
I will, yes, and I'll show the web.
I can set it on. There's somebody who's saying well done, and there's a wow and brilliant slices. So you're getting some good expletives. Okay, David, that just.
Yeah, perfect. And I think I only have a few more things about this and kind of motivating on the things that we don't know. Then I can take more questions and I can very easily show you how you can explore these activities. So one thing that I wanted to point out is that there are other now super bright galaxies in the very early universe. So we were able to discover 5 other. And the 5th one that we found at this redshift, it's in another field that is kind of the other side of the universe. Because it was the 5th at redshift 7, we named it VR7, but also with the explicit intention to name it after Vera Rubin. So I didn't talk about her, but Vera Rubin's work was crucial to actually establish the need for dark matter and just how important it is. And I always find it really depressing that given her tremendous kind of groundbreaking work, that she didn't get a Nobel Prize, and she unfortunately passed away without that happening. But it turns out that VR7 in the ultraviolet, it manages to be even brighter than CR7. So not in this kind of green light that we use to discover it, but in the continuum in the ultraviolet. It's really quite impressive. But these galaxies are still incredibly rare. So you need a big area before you can find one. So we still kind of hold the record for the number of these ones. And we're trying to push these surveys to even longer distances. So essentially even earlier in time. So my PhD student that just started last October, that's what she'll be trying to do, is to beat me and to find CR8. And I'm sure she'll be able to do that. So perhaps one of the most exciting things as well is as we find these galaxies, we have been lucky enough to then be able to point Hubble at them. And I think for me personally, that's been one of the most exciting things. You get an email from the Hubble Space Telescope saying, later today, I will observe your targets after preparing everything. And then while the telescope is observing, you can even follow it on Twitter, and it will tell essentially who is it observing for, what it's pointing at. And typically, whenever I do this with Hubble, people tell me that might be wasting Hubble's time, because if you look at the very center of the cross, there is essentially nothing. And this is not to worry, and it's mostly a consequence of the fact that even though these galaxies are so bright, they're at such high redshift that all the optical light is gone. It has been moved into the infrared. And that is why in these pictures, it always looks like we're looking at just perfect darkness. But when the images come out, they come out with real galaxies. And we've now been able to publish all the results from this Hubble follow-up work. So even though we've kind of made a lot of progress, and I try to give you a perspective of how just 100 years ago, what I do couldn't be done, because we thought that our own galaxy was the full universe, and now we know that there must exist something like 2 trillion galaxies. I hope that you still get the idea that most questions remain unanswered. And I think for me, that is a great thing, because it means that most of the interesting puzzles are still to be done. And it means that there's still a lot of potential for discovery. And this is true at all kinds of cosmic times. Obviously, in the early universe is probably where we'll discover the most unexpected things, because we know about it a little bit less than the present day universe. But sometimes we get surprises like dark matter. And I won't even go into the mysterious thing that seems to be dark energy. But what I think really encapsulates our ignorance is kind of this very simple pie chart, where the slice that actually makes us, or that we're made of, is just a tiny little bit of the entire cake. So everything that we know about, and for example, that particle physics describes, at least at the moment, is only about 5% of the entire universe. Most of the matter, something like 80% of the matter in the universe, is in the form that we cannot see, and somehow we cannot interact with except gravitationally. So in principle, we seem to know how it works, but we don't know what it is. So that's dark matter. But perhaps more troublesome is the fact that about 75% or 70% of the universe is in the form of something that we don't know what it is, and we don't know how it is working. But we think it is a reason why the expansion of the universe, or the reason why space-time is growing at an accelerated rate. And it means that there really is a lot of potential for discovery there. And I think, just to finish and before taking questions, one thing that I really like to highlight is the immense progress. So I've talked mostly about how we can use observations and telescopes to figure out what is happening in the universe as time goes on, but actually using computers, supercomputers, and also actually game consoles working together, putting all the physics there with good programming, has also led to fantastic breakthroughs. So this is just an example of the illusory simulation. So it's kind of a fake universe with a lot of galaxies forming, completely ends off, just testing our understanding of physics, where without any human intervention, essentially galaxies, stars, supermassive black holes, they form, they actually explode a supernova, they produce the chemistry, and you can actually see how these chemical elements get spread with the supernova winds, sometimes even across galaxies. This is how we can tell that some of the carbon and oxygen and iron that's probably part of our bodies might have been done in some other galaxy many billion years ago, because it certainly happens in simulations. And it means that we now have this powerful way, because in a computer simulation, you do have control over time. So you can actually go back in time, check things, and then make time go on and see how things look like at the present epoch. but it means you can also zoom in and then compare with the real universe. I think this is really exciting, and simulations keep getting better and better. And obviously, in simulations, you can see, just like you're seeing now, you can see dark matter because they're put there by default, and you can compare the structure of the universe in dark matter versus the matter that makes us. So with that in mind, I think one of the big messages really is how much we've already discovered, but how much it is still out there to be discovered. And this is one of the big reasons why people like me keep going to telescopes when COVID-19 is not a problem, and trying to essentially improve our understanding of our cosmic origins and the nature of the universe. So I'd be more than happy to take questions now.
David, what I was trying to do there was unmute all the microphones so that we could applaud you, as we would do if we were in an auditorium, but I don't know if that worked. So the way the custom is that you write clap clap in the chat. Let's see the claps come through. There you go. You're getting your applause now. Okay, David, that's brilliant. How fantastic is that? I'm sure there's some questions going to come through. We're still getting claps. So let me just, while there's a question coming through, let me ask, when is the first DS7 going to be discovered?
Oh, yeah, well, I guess if anything, there was one galaxy that kind of has some initials of us, or kind of my students. So that's the galaxy called Masosa. So that comes from it's a very convoluted way that my PhD student came up with a name. It's the first two letters of our surnames. So it was Yorat Mate and Sergio Santos that did that work with me. But at the same time, that galaxy was discovered simultaneously with CR7, and it started as a joke. So the M actually came from Messi, because when we started, it was a joke that it was CR7 and Messi kind of competing to be the brightest galaxy, and Masosa was very small and dwarfy, and CR7 was very big. But in the end, we decided very unanimously to never name galaxies after us, obviously, and to give the honors to, I guess, people that are more worthy of it, like Verrubin.
Oh, very, very noble. Any questions out there? Okay, Tim, I'm going to hand over to you. Tim, can you unmute yourself?
Yeah,
there it is.
I'm trying to get myself going. I did actually have a question, but my chat seemed to run out of space. It was just a general one, again, David, about, is it a basic assumption that you've made in all your work that the laws of physics apply throughout the universe, or is it possible that actually the laws of physics could change and that we just don't know how?
So in general, we do tend to assume that the laws of physics are the same throughout the universe, because we haven't been able to disprove that assumption. There is actually a lot of work in astrophysics to try to see just how much that is true, and perhaps the most important thing, well, I mean, there's tests of, for example, general relativity at different scales, but perhaps the most interesting one has been to try to measure the fundamental constants, so a combination of constants in physics that you can do at very different look-back times. And as far as I know, the constraint is incredibly tight. So it looks like the laws of physics are exactly the same within something like a fraction 0.1% up to now. But obviously we do not know whether that will hold. And I guess we do know that our understanding of physics definitely breaks apart when you go into the regime where gravity is too strong, so very close to black holes, and also when you get to times which are very close to the Big Bang. So those are the two regimes where definitely you cannot assume that the laws of physics are the same in some way, because they kind of break apart.
Lovely, thank you. I see there is one other question from Steve Rosario, which says, at what age were the first galaxies formed that had enough heavy elements to form rocky planets and potentially life?
So that is, well, it's an interesting question. So in our own galaxy, we know that stars that have the most planets are typically the ones which are the most rich in iron. And that is probably, or at least for planets like Jupiter, that's probably because you need some kind of iron core before you can form planets. So it means you would require enough levels of iron to do that. In principle, kind of after the first generation of stars exploded as supernova, they really didn't produce enough iron to do that. So I would think you still require a second generation of stars to form and then go supernova, because before you can actually have a decent chance to form planets, or at least solar systems like our own. So it means you should be looking at maybe something like 1 billion years before that can happen. But maybe in special galaxies that had a lot of gas and material, and where stars formed as early as possible, maybe a few 100 million years. I would say that's the minimum.
Okay, lovely. And a little question I can see from Charmy: are the galaxies expanding as well?
Yes, that's a really good question. And at some point, actually, in theoretical, or some of the theoretical physicists are posing the question whether, if the expansion keeps going, will our bodies even experience it? Will matter just be ripped apart? And as far as we can tell, anything that experiences gravity kind of is able to kind of prevent the space-time expansion. So anything, it means that the space between, for example, our galaxy and Andromeda, they can feel themselves gravitationally. They're actually moving towards each other. Space-time is not expanding in between. So this phenomena of space-time being created and expanding only happens if you do not have masses, essentially, that are gravitationally interacting. If you do, at least even on the scales of galaxies, if they can feel each other, then the expansion of the universe does not win, at least for now. But as it keeps going, it would be possible that even within scales like our own body, space-time could start being created and expanding. As far as we can tell, maybe that is not possible, but we do not know.
Lovely, thank you for that. I've got one question from Ben Simpson, who says, and I think we've had a conversation about a scientist called Rupert Sheldrake together. You will have heard of him, I've no doubt, who is controversial, I think you might say. But you asked at the beginning of your talk, who are we after your research? Do you have an answer you're willing to share with us? Who are we?
Oh, I think, well, my questions were perhaps a little bit easier to address. It was more like where we come from, and I guess clearly 90% is from the stars, and 10% from the Big Bang. So that's basically the simplest answer. So we're 90% stardust, 110% primordial material from the Big Bang. And I guess what we're made of, we can be even more explicit in terms of the different sources of the elements. Now, if we start going into a more philosophical approach that's much harder to address. And also in terms of like what may distinguish life from non-living beings or consciousness, etc. But I will not be going there for now.
No, that's fine. I may say a couple of things about that at the end, but thank you for that. Hazel asked a question for which you're allowed to. There is only one answer, as far as I can see. Is Lancaster the best university in this galaxy?
Of course, yeah. At least in extragalactic astrophysics, of course, yes.
Yeah, quite right. And James, this will probably be the last question, unless anybody else wishes to flash something up. James Chapman asked, what is the current estimate for how long will be until the rate of expansion of the universe exceeds the speed of light? You gave some indication of that, I know, but I've forgotten exactly how long you said.
So as far as we can tell, it's something like 1 trillion years. That is the current best estimate. So it's still a long way to go before. So yeah, so it's about 1 trillion years before we would not be able to see any galaxy beyond the ones that the Milky Way is gravitationally connected to. But of course, my colleagues have already gone and tried to find ways in which future scientists would realize that there's something odd with space outside this kind of local gravitational group, and a way that you might be able to understand that there's other things beyond the darkness would be there's some stars in our galaxy that sometimes get kicked out. For example, when they pass really close or center supermassive black hole, they gain energy and they get out at really large distances, at really large velocities. And some of them can actually escape the galaxy. And in 1 trillion years, this is how extragalactic astrophysics can be done, is by looking at these stars as they get incredibly rare and then they disappear, because they will reach a point where they will go beyond the place where the expansion of space-time is faster than the speed of light, and they will just be gone. So it'll be the way we can do cosmology in 1 trillion years will be very different. But we'll not be able to know that the Big Bang ever occurred, for example.
Wow, fantastic. Oh, Phil Furno has just got something here. We could follow this talk with one from Julie Wardlow. Yeah, we'll think about that in a moment. But could I just ask anybody else who's got any other questions, if you could just put something on chat? I can't see anything else other than the chat, really. Otherwise, I'll wrap up and I'll have a discussion at the end with Phil.
Yeah, and I can. So the other thing that I can do is I can show. Yeah, I guess you should be able to see. Well. Yes. So if you type xgal.uk, you'll be able to go to this website, Time Traveling Through the Universe. This is where you can also find a lot of the videos that I've used in the presentation. There's actually many documentary about the research that we do, also with subtitles and how we time travel through the universe. But most important is the tab with xgal DIY, where you have the different activities that you can do. So you have a step-by-step or full instructions, because it depends on how you want to do it. So the first one, if you click, this will allow you to discover CR7. So the way these things are set up is there's a YouTube video with a background, some of the things that I've covered in the presentation. And you can download the instructions, and the only thing you need, this will work in Windows straight away, is the software. So there's also the link. This is the only thing you need. And then there's an actual video that will explain how you can do this. And this means some background, and then step by step, essentially, how you can discover CR7. So it'll show you. It will show you in the instructions what you can do with the software, what you need to do. So it will show you the where you need to click if you're confused. So if the instructions are not clear enough, the videos are the best because it show you really where you need to click and what you should be looking for in this case. And specifically, you'll be changing between blue light and red light. And for distant galaxies, they should disappear in the blue and they will appear in the red because they're so redshifted. So in a way, for this activity, it's kind of spotting the differences, but you'll be discovering distant galaxies. And at the end, you can also submit the discoveries to us. So you can tell us how many galaxies you found, and you can name your own and provide any further comments. And the other activity you can do is connected with doing a 3D map of the universe. So it'll tell you, so it's a little bit more advanced or with a little bit more physics, again, with a video explaining the physics behind it and how we can do it, and then essentially how to make a 3D map of the universe yourself. And again, with step by step and trying to explain everything you're doing. So I would encourage you to at least give it a go to discovering CR7. And it's even fun for kids because you can play it as spotting the differences. And if you're more interested in calculating some of the quantities like redshift and transforming it to distances, the mapping the universe activity will tell you how to do it and in a way that you can follow the videos and do it without getting lost. If you do have questions, feel free to also email me or let me know if something is unclear. That's what I'd say.
Wow, that's fantastic, David. What an extraordinary resource you've got there. What I'm going to do, I'm not going to take any more questions now because we're 8:45. I'm just going to wrap up and say that to thank you so much for giving us the time and your amazing expertise and your ability to explain all those mind-blowing principles and techniques so clearly to us in ways that a layman can understand. Even people who didn't do Phil's physics tutorial last night would have understood what you said this evening. What I'm proposing to do is we have recorded this whole session, so I'm going to send some of the follow-up link to that recording to all the people on our Cafe Sci list, which is about 250 people, even though only 17 actually clocked in this evening. So they have the opportunity of seeing it in their own time. So it will go, you can be assured, to a wider audience than were able to witness it live this evening. What was the other thing I was going to say? Yes, the visit. Phil asked me to say that he is happy to coordinate the visit to the laboratories, obviously once the lockdown is finished sometime in the autumn. So one of the things I will ask when I send out my note about this evening will be to clock in to say that you would like to be part of the visit. And we'll see how many people we get. And if we have to have 2 or 3 visits hosted by Phil, then he's happy to do that. So that's great. It just reminds me to say, again, a huge thank you. We do have another Cafe Sci online talk booked in for the 30th of April, which is Luke Barnes and Geraint Lewis, who are going to talk about their book called The Cosmic Revolution. You will remember that they were due to do a UK tour around sites in the UK this month, but that obviously got cancelled. And so there's an opportunity of hearing what their book is about and asking questions. And you can even get a signed copy of the book, because I have an electronic signature that we can issue with anybody who wants to buy a copy of their book. So that's on the 30th of April. And any events after the 30th of April are TBC at the moment. But nevertheless, I'm hoping that the feedback from this session, and do provide some feedback, not just on the chat net, but by email preferably, would be very helpful to know whether or not you felt that was as worthwhile. I know you feel it was from those that were there. but to feel that if we can get as much out of future sessions as we got out of this evening, I think it's well worth continuing the online programme for the Cafe Sci. So brilliant. So finally, both Phil and David, thank you so much for all the work you put into making this possible. I'm particularly appreciative of the time. You're a busy person, David. I do appreciate that. But you sounded so relaxed and easy to chat to. I'm sure people will feel able to contact the organisation and hopefully take part in that fantastic resource that you highlighted at the end. So without further ado, if I can ask Phil to close the session off with everybody, and thank you again for watching and listening and taking part. All right, good night to all, and hopefully we'll see some of you again at the next one on the 30th of April. Right, good night. Phil, over to you.